Would you do it now?
Probably. I mean, I survived, so. The purpose behind it, I could not come up with one
No,
now.
I mean,
We just did it, me and my buddies.
Open
your mouth, man.
yeah, yeah. All right, electricity concerns the distribution and movement of electrons. Distribution and movement. And.
Okay.
Yeah,
A-N-D.
A and D. Electrification, on the other hand, is the process of electric charges being added to or subtracted from an object. Now, objects can be considered negatively charged or positively charged. So, if an object is negatively charged, what does it have? More electrons. If an object is positively charged, it has fewer electrons. Yeah. But I like your thinking. Yeah. And what is considered to have no charge? Something called
Neutral.
well, no. Don't think atomically. Let's just think.
Neutral.
What has a zero reference point? Something called, you've all heard this term, ground. Okay, ground. Ground will take what? Charges and what? That's why they shoot them into the ground. Goes into the ground, and the earth has an infinite number of positive and negative charges. Okay, 5 laws of electrostatics. 5 laws of electrostatics. First one is referred to as repulsion attraction. Yeah, you can do that. Like charges do what? Repel. Unlike charges attract, right? Now, this is where I always like to stop and take a minute, and we stop with the science piece of this. Okay, do you know where I'm going?
Mm-hmm.
Huh?
Yeah.
Where am I going?
Magnets.
No!
Oh, okay.
We're going to leave science over here for a minute. We're going to bring in the concept of sociology for just a minute. You know where I'm going? Where am I going?
People. Opposite.
Yes, okay, but specifically dating. Is that true in dating? Opposites attract.
So.
I think you gotta have a good one.
I think my husband and I like the same person.
Huh? Opposites attract. Similar repel. No.
It's kind of like,
I feel like there's a fine balance.
you have to have
between-
some things, but not everything
Okay,
though.
all right. So there are there's room for difference.
Yes. Definitely.
But would you say you'd have to ease more towards similar than opposite? You gotta have more in common than not, right?
Yes.
To what? Coexist. Okay, now we'll bring science back. We had that little discussion. So, the second law of electrostatics is this. I'm gonna draw it up here. I hope you guys recognize it. Well, I'm not known for that. All right? What's that? Yes. Ooh. This is something called the inverse square law. Have you heard of that? Huh? Where'd you ever hear this?
In the 9th grade.
So you were already in radiation therapy. Did you guys cover this? Have you done anything with radiation protection yet?
Protection?
We
Yeah, in
have
terms
a
of
little
the
bit-
distance piece.
Oh,
Okay, you want to be what from the source?
yeah.
Far away, and it's because we know that the inverse square. Now, the inverse square law affects other venues other than radiation. Okay? Here's the inverse square law. The force between two charges is directly proportional to the product of their magnitudes and inversely proportional to the square of the distance between them, period. So in other words, the further you get away, the force is what? Less. The force is less. Inverse square law. If we do it with radiation, we use what? MR.
After?
Number 3, law of electrostatic distribution. All righty, before I give you that, let's get a few terms here. Do you all know the difference between a conductor and an insulator? What does a conductor do? It will move electrons. It will conduct, it will move. An insulator does what? It doesn't produce the movement of electrons. All right. Number 3, distribution. Charges reside on the external surface of a conductor and and distributed equally on non-conductors. So if this is a copper wire, we have a lot of charges on the surface. If this was an insulator, they're all over the place, okay? So you can see now why this would be a good conductor. In other words, they're all on the surface, and when we have something to move them along, they move along. They're all nicely lined up on the surface. That's distribution number 3. Concentration is number 4. Concentration. The greatest concentration of charge will be on the surface where the curve is sharpest. So with that on the table, with our little illustration here, where are we going to have more charges? On A or B?
B.
B, right? We're going to have more charge. What? It's a sharper curve. We're going to have more charges over here than out here. And the last one is number 5, is referred to as movement. Only negative charges can move in a conductor. All right, the laws of electrostatics. Moving along to something called electrification. Objects, you all right?
Yeah, we were just talking about electrification.
Okay, electrification, well, like what? Maybe I have it.
She was like,
No,
said, like,
went
so we
over it.
go over it, I said we just have the definition right now.
Okay, electrification. Objects can be electrified by 3 methods, and I'm sure you're familiar with some of these. Number 1, friction, and I'm open to discussion. Friction, how do things get electrified?
Rubbing together.
Pardon me?
Rubbing together.
All right, so rubbing together. All right, let's let kids give me some examples. Anybody ever lived up north?
Yeah.
All right. What happens this time of year up north?
Very dry and cold.
It's dry, you know, and you walk around. You walk around and you go to reach for a doorknob.
That happens to me down here all the time.
Okay, when?
When you walk in the winter, definitely in the winter.
Okay,
On the carpet.
yeah. You're walking with Yeah, what you're doing is you're picking up electrons. Okay, you're picking up electrons and you go and touch what? A doorknob that has fewer, what happens? You discharge.
Yep. It's like, oh,
All right, so where else does this happen? Or you can, give me some more examples of this.
Like whenever you rub a balloon on your head.
Mhm.
Yeah, you're transferring electrons.
Going down the
Mhm.
slide.
Yeah,
Oh, God.
or you can rub a balloon like on a sweater, or, come on ladies, with the hair, you brought hair in. How else? Combing your hair, brushing your hair, you're transferring
Why do
electrons.
balloons
So with that
do it
friction,
so easily?
so with the,
Why are balloons such a big?
You know, that's a good question.
You know with paper too, like you put a piece of paper on the wall and you just rub it like this, really like for a long time, it'll stick to.
How about in the summertime? Is this so prevalent? It's not really. is it?
not nearly when it's hot,
Why?
maybe moisture.
It's humidity. Humidity kind of blocks it. And you know, moisture is funny that way. What is water? Is water a conductor? So so give me an example that would prove it's a conductor.
Get in the bathtub.
Yeah, that's that scenario, right? You don't listen to a radio plugged in the wall. So there, water's a conductor. Well, is there any scenario where water's an insulator?
I mean, for heat energy, yeah, but specifically for electricity, I can't think of one.
Well, you know these scenarios we just described with rubbing off electrons?
All right. You're up.
Where's a scenario where it might be an insulator? What do people do up north
Igloos?
in the winter to put moisture in the air? They have something called a humidifier. You pour water in it, you put energy, electricity in it, and it gives off moisture, and it gives the environment some moisture. Just as a story on this is, back when we did images with X-ray film, working in a dark room, film is very sensitive material. I think you all know that because you don't want to expose it to what?
Light.
Light, but you don't want to expose it to any type of friction either. So in a dark room, an X-ray film dark room, in the winter, you have to run a humidifier to put moisture in the air as an insulator, because when you're putting just a little movement of taking a piece of film out of a holder, what's that?
Friction.
Friction, and it can discharge, and you're starting with a piece of X-ray film that has static on it. Okay, here's what it would look like.
So with the friction causes you to pick up electrons, and you touch an object that has fewer electrons.
It discharges, yeah.
Why does it do that? Does it balance them out, or do we?
Oh yeah, it wants to equalize.
It equals
Yeah.
out, okay.
So if you have a
So that
radio-
both objects will have the same number of electrons?
Yes. So static would look like this. Okay? So you're starting to take a radiographic image of a patient, and if it has static on it, you're behind the game. It's already got something on it because of the energy and the distribution, the friction. It discharged. It rearranged the electronic scheme on the film. All right, so friction is a method of electrification. All right, so that's just friction. One object, because of movement, picks up an excess number. Another one for electrification is contact, and we already talked about that, is that when you touch something, you make contact, and you do what? You discharge the excess amount of charge. The charges will move from the object with a lot of charge to the object with less charge when we have contact.
And is there a certain amount of electrons that at which it does this for us to feel that static shock?
I would say yes. I don't have a formula or a number, but you know, it has different intensities. You could even discharge something with contact and not even know. Let's face it, this doorknob scenario, does it happen every time? No, it doesn't. But I think it'll happen more if you have a carpeted floor versus this. Because a carpeted floor, we pick up more.
Or if you wear slides with socks on?
Yeah. And the last one is induction. Now, this is where charges act on each other without contact. Okay, so there we have two objects. Which has more charge? Right? Everybody agree? A has more charge. And if you bring A close to B, we have a lot of like charges. And what do like charges do? They repel. So if we did this, all these charges here will do what? No, did we bring A closer? So what do like charges do? So it'll look like this. They'll redistribute they'll repel. Because what? Like charges repel. If we pull A back, it goes back to where? Looking like this. They redistribute back to normal. That's called induction. Contact, induction, friction. Okay. Now we're going to talk about something called electrodynamics. All right, electric current. First thing under electrodynamics, electric current.
Electric or electro?
Electric, T-R-I-C. Electrons that are moving in the same direction. What's that called? Pardon me? It's a current, but it has a name when electrons are moving in one direction.
Beam?
Oh, just think of a conductor. Okay. Flow in one direction, yes. All right, you heard this term. Have you ever heard the term direct current? That's what I'm talking about. Electrons moving in one direction. Give me some examples of things that operate with direct current.
Power lines?
Oh, no,
Not power line?
not power line. I'll give you it's a source.
Wall outlet?
Not a wall outlet.
Next thing.
Source as in like radiation source?
The charger.
It's never works. Oh, there it is. All right. What makes this light come on? What's in here?
Battery?
There's a battery. Batteries operate on direct current. Electrons moving in one direction. Give me some more examples of a battery. A car. Anybody have a dog?
Yeah.
Do you walk it? Huh? Do you ever walk it in the morning? What do you take with you?
Flag,
A what?
a bag.
A bag and a?
Flashlight.
You need the flashlight, right? That's what? That's a battery, okay? Current moving in one direction is direct current versus current moving
Alternating current.
in alternating directions is called
Alternating.
current. We'll get to alternating current in a minute. But let's go back to still direct current. Give me some examples, some more examples. Now we're going to move up from flashlights and stuff. What do you use that uses direct current?
Computer.
Okay, a computer. Right, you plug it in. You plug your laptop in, right?
Electric meter?
And yeah, if you use that source, right? But it's so in other words, a computer, you plug it in the wall, which has what? Alternating current. Okay. Does the computer take alternating current?
No.
It doesn't want that. So what do?
Convert.
We convert the alternating current from the wall to direct current to go through the computer. How's that work?
Is that the brick that does that?
The brick?
Is that what, that's why it's always got such a.
Yeah.
Piece right there, is that what's changing?
This thing here converts the alternating current to direct. Some of them have, I know the one I have at home, I have a, can I touch this? You know, no, we have a little device here in the middle. It looks like a big candy bar.
Yeah.
It changes the alternating to direct. What else requires direct current? X-ray tubes. Okay, X-ray tubes. You'll see that down the road. All right, so let's do a graphical representation. So we have AC, DC, this is a sine wave, which is a graphical representation of alternating current. So, there's your notes. All right, so this is a sine wave of what's happening in a current, okay? Alternating current. Just think of a wire with a bunch of charges on the surface, okay? And this is all that happens with alternating current. 1 minute the electrons will go in this direction, and then they flip, and then they go in which direction? Where's the arrow go?
Yeah.
Towards me?
Yeah.
Okay? All they have to do for all your appliances, think of all the appliances you have in your home, they're plugged into what? Alternating current, and the current goes where? It alternates. The electrons move back and forth. Your appliance doesn't care which way they're going. The fact that they move the light goes on. Okay, the light goes on. That's what alternating current looks like. And there's a point here. Well, what's happening here? And here, and here, and here. What's happening at those dots? No, you were listening. Yeah. There's nothing happening. Okay? So what you see up here, so why don't the lights flicker? Because what you see here is there's a cycle, there's a cycle. So you see what up there? How many cycles? 2. Electricity operates at, this is why your lights don't flicker. Electricity out of the wall operates at, think of this now, 60 cycles per second. Is that fast? That's pretty fast. Things don't have time to what? Flicker. 60 cycles per second. All right, so that's a question for a test. All right, but how many changes in direction per second?
120.
120, right? It's 120. Well, here we have 2 cycles that have what? 1, 2, 3, 4. You know, we can, don't make me draw this. 60 cycles per second. Now, that's what we use in this country. Have you been overseas? Anybody been overseas, like to Europe? What's going on over there? Can you take an appliance from here and plug it in the wall?
No.
Different outlet plugs. Different-
Well, the plugs are different?
Yeah.
What else?
Different charge.
Well, they operate at a different rate, a little faster than, what did I just say? 60 cycles per second.
Yeah.
Their rate's a little faster. Okay, now, when I was in the service, I went overseas. And in those, we had something called records. Okay? That we used a record player. And you just didn't take your record player and plug it in the wall over there. Because it would what? Spin a lot faster, that turntable. You all with me on what's a turntable? So what did you do?
Did you have like the converters?
Huh?
You talking about the old crank one?
No, I'm not that. Oh, God.
Way back.
What's your name again?
How far back are we going here?
No, just.
Well, that one wouldn't be electric, that would be manual.
Yeah.
Well, no, it's a, so when if you plugged it in there, and they're faster than 60 cycles a second, the turntable will spin faster, and what do you think the music sounds like?
Fast.
Like the Chipmunks, okay? So what do we do?
Now they have those little plug
At speed
converters.
adjustment.
Yeah, did
Yeah.
you guys have converters?
Well, yeah, back in my time, they weren't that,
You slow them down?
yeah, you would plug in a transformer. Plug it in from overseas. I was in England, so you'd plug it in the wall. Then you take your appliance, your record player, and plug it into that. And we talked about this a few weeks ago. That was a step-down transformer. It slowed things down. And then there was another way. Without the transformer, you could put some type of a kit on the turntable that would create friction and just do what?
Slow it down.
Slow it down. So, what do you,
And there were some turntables you could actually slow it, you could choose the speed you wanted.
oh yeah, there was 45 RPM, 33 RPM, you're really testing.
Why is it they operate at faster cycles?
I don't know.
That's just what they do.
Yeah.
Because they're just better than us.
Well, they use a metric system too and stuff like that.
You're smarter than us. We figured out how to do it without making shit explode.
Hey, but we still win those wars, don't
Still
we?
in that war, that's right.
We're just physically better than.
All right, so,
Better.
So yeah, that was a step-down transformer. Their power operates a little faster than ours. And what do you, and these transformers, the step-down transformer that I had, you know, was like boat anchor heavy, okay? And what would I do when I transferred back to the States? What do you think you do?
You sold
You
it.
just sell it to the next guy coming along. Yeah, you did that. But, you know, 18 and 19, that's eye-opening. You gotta do something like that. All right, so, then I should probably draw what direct current looks like. Direct current will come up and just look like this.
Oh, nice.
Flowing in one direction, right?
Yes, sir.
That's a battery. What's the most common material used as a conductor?
No.
What kind?
Copper,
Copper.
expensive.
Yep. It's very conducive to electron movement. All right, let's look at some materials that would be considered an insulator and a conductor.
Rubber.
Rubber is what?
Insulated.
Rubber's an insulator. What else?
Dirt,
Okay, yeah. How about plastic? How about glass? These are all insulators. Another example of a conductor other than copper, aluminum. And I have something in my notes here, something called a superconductor, and that is, I'll give you the material. You tell me where else it's found, and that is titanium. Where do we find titanium? In people.
Bodies.
Where?
In bodies.
What, where? Quincy?
In my leg.
Yeah, they're what? Prosthetic devices are made of titanium. And then you've probably all heard the term superconductor, right? That's what they use in what products? Semiconductor? Computers.
Wait, super or semi?
For me?
Is it super or semi? Or both?
Well, super is titanium.
Okay.
Semiconductor is silicon germanium. See the association now with semiconductors, Silicon Valley. Oh, computer folks, okay. All right, let's define electric an electric circuit. It's a pathway, commonly copper wire. That permits electrons to move. All right, and then one last thing, so when you look at a circuit, to make a circuit work, you have to have an excess of charge on one end and a deficient number of charge on the other end, the opposite end, the further end.
So that it'll travel.
You gotta have a what?
Balance.
No. To make electrons flow, you gotta have what?
Negative.
A difference. In other words, you gotta have a surplus at one end and a deficiency at another so that it will, okay? It will go. So where do we have a excess amount of charge? Think big. Think globally. Think big. Think globally. I think I might have drawn it on the board.
Magnetic.
I'm gonna start to draw, and when you recognize when to stop.
It's magnetic field. Is that what you're?
No. All right.
Telephone poles.
Oh, it's a big complex.
Power factory.
There, I heard it.
Oh, power plant.
The power plant is where the what charge is?
Excess.
The excess. You turn on your appliance at home, what are you asking for? Give me some. All right? Give me some. It's gonna pull. So if you turn on your appliances at home, too many at one time, you're asking for what?
Too much.
A lot of that charge. What are you creating? Heat. And then what happens to your appliances?
You're
They blow up.
Things stop, don't they? For what reason?
You're
Too
asking for
much.
too much.
Too much.
Then you have to go
What's
redo
the reason?
Because there's not a
Overloaded
deficiency.
yours.
Oh, you're so close. Why do we
It's
have these
overpowered.
breakers and all that stuff? Why do we have that? For your safety, right? You want a fire? No.
Yeah.
So things get a little hot, and so this is where we'll stop today.
Lots to go there.
We'll get more into, next week, we're gonna get into things like what haven't we talked about that associates with electricity? Voltage, have I used that term? No. Have we talked about amperage?
Yeah.
Have we talked about resistance? No, we're gonna talk about all
It's
that.
great. I
next
was
week.
just thinking about
Pardon me?
voltage. I was just thinking about voltage today.
Voltage?
Yeah. We haven't talked about it.